Right now, as you listen to this, something enormous is happening on the surface of our sun. A dark wound has opened up on that blazing sphere, a region so vast that dozens of Earths could fit inside it with room to spare. Scientists call it a sunspot, but this one is different. This one is so large, so magnetically violent, that researchers around the world are watching it with a mixture of fascination and genuine concern. The question on everyone's mind is simple, and it is terrifying. Could this giant sunspot end life on Earth? Before we dive deeper into this cosmic mystery, if you are enjoying this journey through space, please take a moment to hit that like button and subscribe to Cosmic Drift. We explore the wonders of the universe together. Now, let us return to our sun and the strange dark patch that has captured the attention of the scientific community. To understand why this sunspot matters, we need to understand what the sun actually is. Most of us think of the sun as a giant ball of fire hanging in the sky, but the truth is far more interesting. The sun is not on fire at all. Fire needs oxygen, and space has almost none. Instead, the sun is a massive ball of plasma, a superheated gas, where atoms are torn apart by intense heat and pressure. Deep in its core, hydrogen atoms are being crushed together with such force that they merge into helium. This process releases an almost unimaginable amount of energy. Every single second, the sun converts about 4 million tons of matter into pure energy. That energy fights its way outward over hundreds of thousands of years before finally reaching the surface and streaming out into space as light and heat. The surface of the sun, the part we can see, is called the photosphere. If you could somehow look at it up close without being vaporized, you would see a roiling, bubbling ocean of plasma. Huge columns of hot gas rise from below, spread out across the surface, and then sink back down as they cool. This creates a pattern that looks almost like the skin of an orange, with millions of tiny granules each about the size of a small country. These granules appear and disappear over the course of just a few minutes, giving the sun a constantly shifting living appearance. But every once in a while, something strange happens on this churning surface. Dark patches appear. Regions where the sun seems to be turning off, going cold and dark compared to the blazing plasma around them. These are sunspots, and they have been observed by humans for thousands of years. Ancient Chinese astronomers were among the first to record sunspots. They noticed dark marks on the face of the sun when dust storms or thick haze allowed them to look at it directly without going blind. European astronomers began studying them carefully in the early 1600s, right after the telescope was invented. Galileo himself tracked sunspots across the face of the sun, proving that our star rotates on its axis. But for centuries, no one really understood what caused these mysterious dark regions. Today, we know that sunspots are all about magnetism. The sun is not just a ball of hot gas. It is also an incredibly powerful magnet. But unlike the simple bar magnets you might have played with as a child, the sun's magnetic field is unbelievably complex and constantly changing. The sun rotates, but it does not rotate like a solid ball. Its equator spins faster than its poles. This differential rotation stretches and twists the magnetic field lines that run through the sun's interior. Over time, these field lines get wound tighter and tighter, like a rubber band being twisted over and over again. Eventually, bundles of these magnetic field lines become so concentrated and so powerful that they push through the surface of the sun. When this happens, something remarkable occurs. The magnetic field in that region becomes so strong that it actually suppresses the normal convection currents that bring hot plasma up from below. Think of it like putting a dam in a river. The hot material that normally rises up to replace cooling plasma is blocked. Without that fresh supply of heat, that patch of the sun's surface cools down. It might still be thousands of degrees hot, but compared to the surrounding plasma at nearly 10,000 degrees, it appears dark. That is what a sunspot is. It is not actually dark at all. If you could pluck a sunspot out of the sun and hang it in space by itself, it would glow brilliantly, far brighter than 1,000 full moons. It only looks dark because the area around it is so much brighter. The sunspot currently worrying scientists follows this same basic pattern, but its size is what makes it remarkable. Most sunspots are about the size of Earth, give or take. Some are smaller, some are larger. But this one has grown to many times the diameter of our entire planet. If you could somehow transport Earth to the surface of the sun and set it down in the middle of this sunspot, our world would look like a marble sitting in the middle of a dinner plate. Size matters when it comes to sunspots, and the reason has to do with those twisted magnetic field lines we talked about earlier. Remember how they get wound up and stretched by the sun's rotation? Well, the bigger the sunspot, the more magnetic energy is stored in those field lines. Think of it like a giant spring being compressed. The more you compress it, the more potential energy you store, and eventually, that spring is going to release. When the magnetic field lines in a sunspot become too twisted, too strained, they can suddenly snap and reconnect in a different configuration. This releases all that stored magnetic energy in a catastrophic burst. Scientists call this event a solar flare. A solar flare is like a bomb going off on the surface of the sun. In just a few minutes, it can release as much energy as billions of nuclear weapons detonating simultaneously. The temperature in the flare region can spike to tens of millions of degrees, far hotter than the core of the sun itself. This superheated plasma emits a blast of radiation across the entire electromagnetic spectrum, from radio waves to visible light to ultraviolet to X-rays and even gamma rays. That radiation travels at the speed of light. It reaches Earth in just 8 minutes. There is no warning, no time to prepare. One moment everything is normal, and 8 minutes after a major flare erupts, a wave of radiation is washing over our planet. But solar flares are not the only danger lurking in giant sunspots. There is something else, something even more potentially devastating. It is called a coronal mass ejection, or CME for short. To understand what a CME is, you need to know about the corona. The corona is the outermost layer of the sun's atmosphere. You might have seen pictures of it during a total solar eclipse. That beautiful white halo of light surrounding the darkened sun. The corona is incredibly hot, millions of degrees, far hotter than the surface of the sun itself. Scientists are still working to understand exactly why it is so hot, but they know that magnetic activity plays a major role. When a solar flare erupts, it does not just release radiation. It can also launch a massive cloud of solar plasma into space. This is the coronal mass ejection. Picture 1 billion tons of superheated gas, threaded with tangled magnetic field lines, being hurled away from the sun at speeds of up to several million miles per hour. Some of these ejections expand outward in random directions, posing no threat to Earth. But others are aimed directly at us. Unlike the radiation from a solar flare, which arrives almost instantly, a CME is physical matter traveling through space. Depending on how fast it is moving, it can take anywhere from 15 hours to several days to reach Earth. This gives us some warning time, but not much. And when a CME arrives, the consequences can be severe. Earth is protected by its own magnetic field, a bubble of magnetism generated by currents of molten iron in our planet's core. This magnetic field extends far out into space, deflecting most of the charged particles that stream constantly from the sun in the solar wind. Without this protective shield, the solar wind would gradually strip away our atmosphere, leaving Earth as barren and lifeless as Mars. But the magnetic field has its limits. When a powerful CME arrives, it slams into Earth's magnetosphere like a tsunami hitting a seawall. The magnetic field gets compressed on the side facing the sun and stretched out on the opposite side into a long tail. If the CME's magnetic field is oriented in just the wrong way, it can partially cancel out Earth's protective field, allowing huge amounts of energy and charged particles to pour into our atmosphere. This is when things get dramatic. Those charged particles funnel down toward the poles, following Earth's magnetic field lines. When they hit the upper atmosphere, they collide with oxygen and nitrogen atoms, exciting them and causing them to glow. This is what creates the aurora, the northern and southern lights that dance across the sky in rippling curtains of green and red and purple. A powerful CME can push the aurora far beyond its normal polar home, allowing people at much lower latitudes to witness this spectacular light show. But the aurora is just a beautiful side effect. The real danger is what happens on the ground. When all that energy pours into Earth's magnetosphere, it generates electric currents in the upper atmosphere. These currents, in turn, induce currents in any long conductor on Earth's surface. Power lines, pipelines, telecommunications cables, railroad tracks, anything that stretches for miles becomes an antenna, picking up these geomagnetically induced currents. For most of human history, this was not a problem. There were no power lines, no pipelines, no telecommunications networks. A major CME would create spectacular auroras and perhaps make compass needles spin wildly, but life went on as normal. That changed in 1859. In late August and early September of that year, a British astronomer named Richard Carrington was sketching sunspots when he witnessed something no one had ever seen before. A brilliant white light flared up in the middle of the sunspot group he was observing. It lasted for about 5 minutes before fading away. Carrington had just witnessed a solar flare. What Carrington did not know was that the flare had launched a massive CME directly at Earth. The ejection was traveling unusually fast, propelled by the explosion that Carrington had observed. It reached Earth in just 17 hours. The effects were unprecedented. Aurora displays lit up the sky all over the world. People in Cuba, Hawaii, and Colombia saw the northern lights for the first time. The glow was so bright that people in the northeastern United States could read newspapers by its light at midnight. Gold miners in the Rocky Mountains woke up and started making breakfast, convinced that dawn had arrived. But the real chaos was happening to the telegraph system, the internet of its day. Telegraph operators reported that their equipment was sparking and catching fire. Messages were being garbled or lost entirely. In some cases, operators found that they could send and receive messages even after disconnecting their batteries. The geomagnetic currents were so strong that they powered the equipment all by themselves. This event became known as the Carrington event, and it remains the most powerful geomagnetic storm in recorded history. At the time, the damage was relatively limited. Telegraph systems were the most advanced technology of the age, and while they were disrupted, society did not depend on them completely. Life could go on without instantaneous long-distance communication. But imagine if a Carrington-class event happened today. Our world is completely different from the world of 1859. Everything runs on electricity. Our power grids span entire continents, with transmission lines stretching for thousands of miles. Our communications depend on satellites orbiting overhead, fiber optic cables crisscrossing the ocean floors, and cell towers dotting every landscape. Our banks, hospitals, transportation systems, water treatment plants, and food distribution networks all depend on the continuous flow of electrical power. If a massive CME hit Earth today with the same intensity as the Carrington event, the results could be catastrophic. The first systems to fail would be satellites. Most satellites are designed to withstand the normal space environment, including routine solar activity. But an extreme CME can overwhelm their radiation shielding, frying delicate electronics and damaging solar panels. Within hours of a major impact, GPS satellites could start failing. Communications satellites could go silent. Weather satellites could stop transmitting data. The space-based infrastructure that our modern world depends on could be knocked out in a single day. On the ground, the surging currents induced by the geomagnetic storm would target the weak points of our power grid. The most vulnerable components are large transformers, the massive devices that step voltage up and down to move electricity efficiently over long distances. These transformers are custom-built, extremely expensive, and have lead times of months or even years for replacement. If a significant number of them were damaged simultaneously, entire regions could lose power for extended periods. Studies have suggested that a worst-case scenario could leave parts of the United States, Europe, and China without power for weeks or even months. Think about what that would mean. No lights, no heat or air conditioning, no refrigeration for food or medicine, no way to pump gasoline, no way to access money from banks, no cell phones, no internet, no television. Hospitals running on backup generators until the fuel runs out. Water treatment plants unable to function. The cascading effects would be severe. Food would spoil without refrigeration. Medical equipment would fail. Transportation would grind to a halt as gas stations ran out of fuel they could not pump. Communications would collapse. In the chaos, civil order could break down. Estimates of the economic damage from such an event range from $1 trillion to $2 trillion in the first year alone. Some experts warn that a truly extreme geomagnetic storm could cause societal disruption on a scale not seen since major wars or pandemics. This is why scientists are watching the current giant sunspot so closely. We are entering a period of heightened solar activity. The Sun follows an approximately 11-year cycle of activity. During the minimum of this cycle, sunspots are rare and the Sun is relatively quiet. During the maximum, sunspots appear frequently and the chances of major flares and CMEs increase dramatically. Right now, we are approaching or near the peak of solar cycle 25. The Sun is waking up. Giant sunspots like the one currently visible are more common during solar maximum, and the bigger the sunspot, the more energy it can potentially release. Scientists are not predicting with certainty that this particular sunspot will produce a dangerous eruption. The Sun is notoriously difficult to forecast. A sunspot might produce dozens of moderate flares and then fade away peacefully. Or it might suddenly unleash a massive X-class flare and an Earth-directed CME with little warning. What we do know is that large sunspots are capable of producing extreme events. And we know that our modern civilization is more vulnerable to such events than at any point in human history. So let us return to the question that brought us here. Can this giant sunspot end life on Earth? The answer is both reassuring and troubling. No, a solar event cannot end life on Earth, not in the biological sense. The Sun has been doing this for billions of years. Our planet has weathered countless solar storms throughout its history. The magnetic field and the atmosphere together provide enough protection that even the most extreme solar event would not directly kill life on Earth through radiation or charged particles. The ozone layer absorbs most harmful ultraviolet radiation. The magnetic field deflects most charged particles toward the poles. We would see spectacular auroras. We might experience increased radiation exposure at high altitudes and near the poles. But life itself would go on. However, and this is the troubling part, a major solar event absolutely could end our way of life, at least temporarily. The technological civilization we have built over the past century and a half is remarkably fragile in the face of space weather. A Carrington class or larger event could knock out power grids across large portions of the planet, disable satellites, disrupt communications, and trigger an economic and social crisis unlike anything in living memory. Some researchers have tried to estimate how likely such an event is. Studies suggest that there is roughly a 1 to 12% chance of a Carrington-class storm occurring in any given decade. Over a human lifetime, the cumulative odds become significant. It is not a question of if such an event will happen, but when. The good news is that we are not defenseless. We are far better at monitoring the Sun than we were in 1859 or even a few decades ago. A fleet of spacecraft keeps constant watch on our star, tracking sunspots, monitoring magnetic field configurations, and detecting the first signs of flares and CMEs. When a major eruption occurs, we can often provide warnings ranging from minutes for radiation to hours or days for CMEs. This gives us time to take protective measures. Satellite operators can put their spacecraft into safe mode, protecting sensitive electronics. Airlines can reroute flights away from polar regions where radiation exposure is highest. Power grid operators can take transformers offline or reduce load to minimize the risk of damage from induced currents. Space agencies can alert astronauts on the International Space Station to take shelter in more shielded areas of the station. But our protective measures are still limited. We cannot stop a CME from hitting Earth any more than we can stop a hurricane. We can only try to get out of its way and protect our most vulnerable systems. And there is always the possibility of being caught off guard, of a fast-moving CME arriving before we have time to fully prepare. The scientific community is working on improving our understanding and forecasting capabilities. New models are being developed to predict solar activity more accurately. New satellites are being planned to provide better observations of the Sun and earlier warnings of approaching threats. Engineers are exploring ways to make our power grids and other infrastructure more resilient to geomagnetic storms. Perhaps most importantly, there is growing awareness of this threat among policymakers and the public. For a long time, space weather was a niche concern, something that only astronomers and satellite operators worried about. But as our dependence on technology has grown, and as we have witnessed increasingly powerful solar events in recent years, the conversation is changing. Governments are starting to take space weather seriously as a potential threat to national security and economic stability. Let us step back now and consider the bigger picture. The Sun is the source of all life on Earth. Without its light and heat, our planet would be a frozen, lifeless rock. Every plant, every animal, every breath we take ultimately depends on energy that began its journey in the fusion furnace at our star's core. We owe everything to the Sun, but the Sun is also wild and unpredictable. following rhythms and cycles that we are only beginning to understand. It is not the steady, unchanging beacon that ancient peoples imagined. It is a dynamic, violent place, with magnetic storms that dwarf anything on Earth, with explosions that release more energy in a few minutes than humanity has used in its entire history. For most of Earth's history, this did not matter to life on the surface. Evolution shaped organisms to thrive under the sun's light, protected by the magnetic field and atmosphere from its more dangerous moods. But now, for the first time, we have built a civilization that reaches up into space, that wraps the globe in electronic networks, that depends on delicate technologies vulnerable to the whims of our star. We have made ourselves vulnerable to the sun in ways our ancestors never were. And now we must learn to live with that vulnerability, to understand the risks and prepare for them while continuing to enjoy the benefits of our technological age. The giant sunspot currently crossing the face of the sun is a reminder of this reality. It may pass quietly, producing nothing more than a few moderate flares that create beautiful auroras in the Arctic and Antarctic. Or it may erupt violently, sending a wave of energy and matter toward Earth that tests our defenses and reminds us of our fragility. Either way, it is worth watching. It is worth understanding. Because the sun will always be there, doing what it has done for 4.5 billion years, following its own rhythms regardless of what we build on our little blue world below. Let us now explore more deeply the mechanics of what happens when the sun erupts. Understanding this process will help us appreciate both the beauty and the danger of our star. When magnetic field lines in a sunspot become sufficiently twisted and unstable, they can undergo a process called magnetic reconnection. This is one of the most violent processes in the universe. Imagine two powerful magnets with their north poles facing each other. They repel each other with tremendous force. Now imagine that they are somehow forced together anyway. The magnetic field lines have to go somewhere, and they reconfigure in a sudden, explosive way. In the sun, this reconnection releases the energy that was stored in those twisted field lines. Some of that energy accelerates charged particles, protons and electrons, to enormous speeds. Some of it heats the surrounding plasma to tens of millions of degrees, and some of it goes into the electromagnetic radiation we detect as a solar flare. The first sign of a flare is often a sudden brightening in extreme ultraviolet and X-ray light. Specialized satellites watching the sun can detect this almost instantly. The flare is classified according to its peak brightness in X-rays. The weakest flares are A-class and B-class, barely detectable against the background. C-class flares are small but noticeable. M-class flares are moderate and can cause minor impacts on Earth. X-class flares are the most powerful, capable of causing serious disruption to technology and even affecting the upper atmosphere. But the classification system is logarithmic, meaning each letter represents a tenfold increase in power. An X10 flare is 10 times more powerful than an X1 flare, and flares can exceed X10. The most powerful flare ever recorded in November 2003 was so strong that it saturated the detectors on the GOES satellites that monitor solar X-rays. Scientists had to estimate its actual intensity based on other observations. They concluded it was somewhere around X45, making it hundreds of times more powerful than a typical X-class flare. When such a powerful flare occurs, the radiation it produces reaches Earth in just over 8 minutes, the time it takes light to travel the roughly 93 million miles from the Sun to our planet. This radiation affects the upper atmosphere, temporarily increasing the ionization of the ionosphere. the layer of charged particles high above the surface. This can disrupt radio communications, particularly high-frequency radio signals that bounce off the ionosphere to travel long distances. During a major flare, radio blackouts can affect large portions of the sunlit side of Earth. The radiation can also pose a hazard to astronauts in space and even to passengers and crew on high-altitude aircraft flying polar routes. During extreme events, airlines sometimes reroute flights to avoid this increased radiation exposure. But as we discussed earlier, the radiation from a flare is just the first wave. The second wave, the coronal mass ejection, is often the more dangerous one for our technology on the ground. Not all flares produce CMEs, and not all CMEs are associated with flares. They are related but distinct phenomena. However, the most powerful CMEs often accompany major flares, and these are the events that cause the most concern. When a CME erupts, a massive bubble of plasma begins expanding outward from the Sun. This bubble can contain billions of tons of material, all traveling at speeds that would be considered impossibly fast by earthly standards. A slow CME might amble through space at a leisurely few hundred kilometers per second. A fast one can exceed 2,000 kilometers per second, more than 4 million miles per hour. The CME carries with it the magnetic field configuration from its source region on the Sun. This embedded magnetic field is crucial in determining how severely the CME will affect Earth when it arrives. If the CME's magnetic field is oriented in the same direction as Earth's magnetic field, the interaction is relatively gentle. The two fields push against each other, but they do not connect. The CME washes over Earth's magnetosphere like water flowing around a rock in a stream. But if the CME's magnetic field is oriented opposite to Earth's field, something very different happens. The two fields can connect through a process called magnetic reconnection, the same process that triggers flares on the Sun. When this happens on the boundary of Earth's magnetosphere, it opens a breach in our planetary shield. Energy and particles from the CME pour through this breach and into the upper atmosphere. The result is a geomagnetic storm. The entire magnetic field of Earth begins to oscillate and fluctuate as it absorbs and releases the energy from the CME. Charged particles spiral down toward the poles, colliding with atmospheric gases and creating the aurora. Electric currents flow through the upper atmosphere and induce corresponding currents in conductors on the ground. Geomagnetic storms are measured on a scale from G1 to G5, with G5 being the most severe. A G1 storm might cause weak power grid fluctuations and minor impacts on satellite operations, along with auroras visible at high latitudes. A G5 storm can cause widespread power system problems, complete high-frequency radio blackouts on the sunlit side of Earth, satellite navigation errors that can last for days, and auroras visible as far south as Florida or Texas. The Carrington event of 1859 would have been well off the high end of this scale. Some researchers estimate it was the equivalent of a G6 or G7 storm, if such categories existed. Modern civilization has never experienced a storm of that magnitude. The closest we have come in recent memory was the geomagnetic storm of March 1989. A powerful CME struck Earth's magnetosphere and triggered a G5 storm. In Quebec, Canada, the entire power grid collapsed in just 90 seconds. 6 million people lost power for up to 9 hours. Transformers in New Jersey were damaged. The cost of the blackout and related damage was estimated at over $2 billion. Since then, there have been several near misses. In July 2012, a massive CME erupted from the Sun, that was comparable to the Carrington event. Had it occurred just a week earlier, it would have been aimed directly at Earth. Instead, it missed us, passing through the region of space where Earth had been in its orbit just days before. We never felt a thing, but the event was a wake-up call for scientists who study space weather. There is another factor we should consider in understanding why solar activity matters so much now. Our Sun is about halfway through its expected lifespan. It formed roughly 4.5 billion years ago from a collapsing cloud of gas and dust, and it will continue fusing hydrogen into helium for another 5 billion years or so, before exhausting its fuel and evolving into a red giant. On this cosmic timescale, the variations we observe, the 11-year sunspot cycle, the occasional massive flare or CME, are just tiny fluctuations in a remarkably stable energy source. But those tiny fluctuations matter enormously to us because of our short timescales and our dependence on sensitive technology. A variation that is utterly insignificant from the perspective of the Sun's billions of years of existence can mean the difference between a normal day and a civilization-altering catastrophe for humanity. This mismatch of timescales is something we should keep in mind as we develop new technologies and expand our presence in space. We are increasingly dependent on systems that operate outside the protection of Earth's atmosphere and magnetic field. Astronauts on the International Space Station are much more vulnerable to solar radiation than people on the ground. Future colonists on the Moon or Mars will face even greater challenges, as neither body has a significant magnetic field to deflect charged particles. The current focus on returning humans to the Moon and eventually sending them to Mars makes understanding and predicting solar activity more important than ever. A major solar event during a crewed mission to Mars, when astronauts are exposed to deep space radiation for months at a time, could be life-threatening. Space agencies are working hard to develop better forecasting tools and more effective radiation shielding to protect astronauts from these hazards. Let us return now to the giant sunspot that prompted our exploration. What do scientists actually see when they look at this feature through their telescopes and instruments? The sunspot appears as a dark region against the brighter surface of the Sun. At its center is the darkest part, called the umbra. This is where the magnetic field is strongest and most vertical, punching straight up through the surface. The umbra is surrounded by a lighter region called the penumbra, where the magnetic field is more inclined and the suppression of a convection is less complete. Through a powerful telescope, the penumbra shows a beautiful striated pattern, like the threads of a rope radiating outward from the central darkness. The size of the sunspot is measured in terms of its area on the Sun's visible disk. Scientists use a unit called a millionth of the solar hemisphere. A typical sunspot might cover a few hundred millionths. A large sunspot might cover a few thousand millions. The giant sunspot currently being observed covers many thousands of millions, making it one of the largest of the current solar cycle. But size alone does not determine a sunspot's potential for eruption. What matters most is the complexity of its magnetic configuration. Sunspots are classified according to a system developed by the Mount Wilson Observatory in the early 20th century. The simplest configuration, called alpha, is a single spot with a single magnetic polarity, either north or south. A beta configuration has two spots of opposite polarity, like the two poles of a bar magnet. These can produce flares, but typically not the most extreme ones. The configurations that worry scientists the most are the complex ones, particularly delta configurations. In a delta sunspot, Regions of opposite magnetic polarity are so close together that they are contained within a single penumbra. This means the magnetic field must be extremely contorted. Like a pretzel twisted back on itself, the energy stored in such a configuration can be enormous, and when it releases, the resulting flare can be correspondingly powerful. The current giant sunspot has been classified as having a complex magnetic configuration, which is part of why it is receiving so much attention. Scientists are monitoring it constantly, tracking changes in its shape, size, and magnetic field orientation. They are watching for signs of instability that might precede a major eruption. Modern observations of the Sun are far more detailed and comprehensive than anything available to previous generations. A fleet of spacecraft observes our star from multiple vantage points. The Solar Dynamics Observatory, launched in 2010, takes detailed images of the Sun in multiple wavelengths of light every few seconds. The Solar and Heliospheric Observatory, a joint project between NASA and ESA, has been watching the Sun since 1995 and can detect CMEs as they leave the Sun and head out into space. The Parker Solar Probe is actually flying through the outer atmosphere of the Sun itself, making measurements that were impossible before. Ground-based observatories contribute as well. Networks of solar telescopes around the world ensure that the Sun is being watched continuously as Earth rotates. When one observatory experiences nightfall, others take over the watch. Computer systems process the flood of data, flagging potential events for human review. Despite all this observation capability, forecasting solar activity remains challenging. The Sun is immensely complex, and we are still learning the rules that govern its behavior. Scientists can say with confidence that a large, complex sunspot like the current one has the potential to produce major flares and CMEs, but they cannot say with certainty whether it actually will, or when, or how powerful the eruptions might be. This uncertainty is frustrating for those who want clear answers about whether to worry. But it is the honest state of our knowledge. The Sun is a dynamic, chaotic system, and some degree of unpredictability is inherent in its nature. What we can say is that the risk is real and non-trivial. We should take it seriously without panicking. The odds of a catastrophic solar event in any given year are low, but over time they add up. Preparing for space weather is similar to preparing for other natural disasters like earthquakes or hurricanes. We cannot prevent them, but we can build more resilient systems and develop better warning and response capabilities. There is something deeply humbling about contemplating our relationship with the Sun. We tend to think of ourselves as masters of our world, capable of reshaping the environment to suit our needs. We build cities, connect continents with networks of communication and transportation, and send robots to explore other planets. Our technological achievements are genuinely impressive, but all of it, every bit of our civilization, exists at the pleasure of a star that pays us no attention whatsoever. The Sun does not know we exist. It does not care whether its magnetic tantrums disrupt our power grids or fry our satellites. It is simply following the physics of plasma and magnetism that have governed its behavior for billions of years. This is not a cause for despair. Rather, it is an invitation to humility and wonder. We are small creatures living on a small world orbiting an ordinary star. The forces that shape our star and our solar system are vastly more powerful than anything we can muster. Yet we have the remarkable ability to understand these forces, to predict them to some degree, and to adapt to them. The story of life on Earth is the story of organisms adapting to the challenges posed by their environment. For billions of years, that environment was shaped by the Sun's light and warmth. by the protective cocoon of the atmosphere and magnetic field, by the cycles of day and night, and the changing seasons. Life evolved to thrive within these constraints, taking advantage of the energy provided while avoiding the dangers. Now we are writing a new chapter in that story. We are extending our reach beyond the protective bubble of our planet, building technologies that operate in the harsh environment of space, making ourselves both more capable and more vulnerable. The challenge for our generation and those that follow is to learn how to do this wisely, respecting the power of the forces we are engaging with, while continuing to push the boundaries of what is possible. The giant sunspot on the sun right now is a small part of this larger story. It will cross the face of the sun over the course of about 2 weeks as our star rotates on its axis. It may produce spectacular fireworks, or it may fade quietly away. Either outcome will add to our knowledge of how the sun works and help us prepare for future events. Whatever happens, the sun will continue doing what it has always done, converting hydrogen to helium, generating magnetic fields, ejecting plasma into space, and warming the little blue world that orbits around it at just the right distance for liquid water and life to exist. We are passengers on that world, beneficiaries of the sun's energy, and, increasingly, subjects of its moods. Let us consider now the protective systems that stand between us and the sun's more violent outbursts. First and most fundamental is Earth's magnetic field. This invisible shield is generated deep within our planet, where the molten iron outer core flows in complex patterns driven by convection and the planet's rotation. These flows generate electric currents, and the electric currents generate magnetic fields. The result is a dipole field, somewhat like a bar magnet, with a north pole and a south pole roughly aligned with Earth's rotation axis. The magnetic field extends thousands of miles into space, creating a region called the magnetosphere. The shape of the magnetosphere is constantly being sculpted by the solar wind, the continuous stream of charged particles flowing outward from the sun. On the side facing the sun, the magnetosphere is compressed to a distance of about 10 Earth radii, roughly 40,000 miles above the surface. On the night side, it stretches out into a long tail extending hundreds of Earth radii. When a CME arrives, it compresses the magnetosphere even further. In extreme events, the boundary can be pushed down to just a few Earth radii, bringing the outer edge of our magnetic shield closer to the planet than geosynchronous orbit, where many communications and weather satellites operate. This exposes these satellites to the full fury of the solar plasma. But even when the magnetosphere is pushed back, it continues to provide protection to the surface below. Charged particles from the CME do not travel in straight lines. They spiral around magnetic field lines, trapped in looping paths. Most of them are diverted around Earth, rather than striking the surface directly. The particles that do make it into the magnetosphere tend to follow the field lines toward the poles, which is why the aurora appears primarily at high latitudes. The second layer of protection is Earth's atmosphere. Even if charged particles reach the top of the atmosphere, they still have a long way to go before reaching the surface. The atmosphere is hundreds of miles thick, a substantial shield of gas that absorbs and scatters incoming radiation and particles. Solar X-rays and extreme ultraviolet radiation are absorbed high in the atmosphere, in a region called the ionosphere. This is why solar flares can disrupt radio communications. The sudden increase in ionization changes the reflective properties of the ionosphere, interfering with radio waves that bounce off this layer to travel long distances. More energetic particles, like solar protons accelerated to high speeds during flares, can penetrate deeper into the atmosphere. The most energetic ones can reach down to aircraft cruising altitudes, which is why airlines monitor solar activity and sometimes reroute flights during major events. But even these particles are mostly stopped before reaching the ground. What does reach the ground is the beautiful glow of the aurora and, more problematically, the induced electric currents in long conductors that we discussed earlier. The atmosphere does nothing to stop these geomagnetically induced currents because they are not coming from space. They are generated locally by the fluctuating magnetic field itself. This is the Achilles heel of our technological civilization. We have built systems that are, in a sense, too good at their job. Power lines efficiently transmit electricity over thousands of miles. That same efficiency makes them excellent antennas for picking up the electrical disturbances caused by geomagnetic storms. Oil and gas pipelines carry fuel across continents. They are equally good at carrying unwanted currents induced by space weather. Our infrastructure is a giant collector for the electrical energy that geomagnetic storms deposit in our environment. Engineers and scientists have been working on ways to harden our infrastructure against these threats. Some approaches involve installing devices that can block or divert geomagnetically induced currents before they damage transformers. Others involve designing transformers that are more resistant to damage. Still, others focus on operational procedures, ways to reduce the vulnerability of the grid by reconfiguring it during a storm. Progress has been made, but there is still much work to do. The electrical grid has grown organically over more than a century, with countless different components made by different manufacturers to different specifications. Hardening all of it against a worst-case space weather scenario would be enormously expensive. Decisions about how much to invest in this kind of protection involve difficult trade-offs between cost, risk, and competing priorities. There is also the challenge of international cooperation. Space weather does not respect national boundaries. A geomagnetic storm affects the entire planet, or at least the entire sunlit hemisphere and polar regions simultaneously. But the infrastructure that it threatens is owned and operated by countless different entities in different countries with different standards and regulations. Coordinating a global response to a global threat is inherently difficult. Fortunately, there are international efforts underway to address this. The International Space Environment Service coordinates space weather monitoring and forecasting among different national agencies. The United Nations has recognized space weather as a hazard requiring international attention. Governments are beginning to include space weather in their assessments of national risk and disaster preparedness planning. Let us take a moment to appreciate the remarkable fact that we can even have this conversation. For all of human history, until very recently, the sun was beyond our understanding. Ancient peoples worshipped it as a god, and rightly so in a sense, because everything they valued depended on its light and warmth. But they had no idea what it actually was or how it worked. Even after the scientific revolution, the sun remained mysterious. Scientists debated its composition, its source of energy, its age. It was not until the 20th century that we understood that the sun is powered by nuclear fusion, converting hydrogen to helium in its core. It was not until the space age that we could send instruments above the atmosphere to observe the sun in wavelengths that do not reach the ground. It was not until very recently that we developed the sophisticated models and observational capabilities that let us study solar activity in detail. We are the first generation of humans to understand, at least in broad terms, what the sun is, how it works, and what happens when it misbehaves. We are also the first generation to build a civilization that is genuinely vulnerable to solar activity. This is a remarkable conjunction of circumstances. We have both the vulnerability and the knowledge to do something about it. Whether we rise to that challenge remains to be seen. The threat from space weather is real, but not immediate, in the way that a pandemic or a war is immediate. It is easy to put off thinking about something that might happen someday, when there are urgent problems demanding attention today. But the scientists who study the sun will continue their work, watching and waiting, building their models and improving their forecasts, hoping that when the big one comes, we will be ready. As we continue exploring the relationship between our sun and our planet, let us consider some of the more unusual effects that solar activity can have on Earth and the life it supports. One of the most surprising discoveries of recent decades is that solar activity may influence Earth's climate. This is a controversial and still actively debated topic, separate from the question of human-caused climate change, which is driven primarily by greenhouse gas emissions. The potential solar influence operates through different mechanisms and affects the climate in different ways. The most direct effect is through changes in the total energy output of the sun. Over the course of the 11-year solar cycle, the sun's brightness varies by about 0.1%. That might not sound like much, but it corresponds to a significant amount of energy when you are talking about the total output of a star. During solar maximum, when sunspots are most numerous, the sun is actually slightly brighter overall, not dimmer. This is because the bright regions called faculae that surround sunspots more than compensate for the darkness of the spots themselves. This small variation in solar output does affect Earth's climate slightly. The effect is measurable but modest, much smaller than the climate impact of human greenhouse gas emissions. However, there may be additional, more subtle ways that solar activity influences climate. One hypothesis involves cosmic rays, high-energy particles from deep space that constantly bombard Earth. The sun's magnetic field, which strengthens during solar maximum, deflects some of these cosmic rays away from the inner solar system. When solar activity is low, more cosmic rays reach Earth. Some scientists have proposed that these cosmic rays might influence cloud formation in the atmosphere, potentially affecting climate. This hypothesis remains controversial, and the evidence for it is mixed. Another possible mechanism involves the absorption of ultraviolet radiation in the stratosphere. The sun's ultraviolet output varies more than its total brightness over the solar cycle, increasing significantly during solar maximum. This ultraviolet radiation is absorbed by ozone in the stratosphere, warming that layer of the atmosphere. Changes in stratospheric temperature can, through complex pathways, influence weather patterns in the lower atmosphere. These potential solar influences on climate operate on timescales of years to decades, much shorter than the geological timescales over which Earth's climate has varied in the past. They are also much smaller than the dominant factor driving current climate change, which is the rapid increase in atmospheric carbon dioxide from burning fossil fuels. But they add an additional layer of complexity to our understanding of the climate system. There is evidence from ice cores and other records that periods of prolonged low solar activity in the past have coincided with cooler climate periods on Earth. The most famous example is the Maunder minimum, a period from about 1645 to 1715, when sunspots virtually disappeared. This coincided with some of the coldest decades of the Little Ice Age in Europe. However, establishing a clear cause and effect relationship is difficult because many factors influence climate, and the correlation might be partly or wholly coincidental. Beyond climate, there are other ways that solar activity can affect life on Earth. The increased radiation during solar storms can have biological effects, particularly for organisms at high altitudes or in space. Astronauts receive increased radiation doses during major solar events, which is one reason why forecasting such events is so important for crewed space missions. High-altitude aircraft passengers and crew also receive increased exposure, though the doses are much smaller than what astronauts experience. There have even been studies suggesting that solar activity might affect human health and behavior on the ground, though the evidence for such effects is much weaker and more controversial. Some researchers have claimed correlations between solar cycles and various human phenomena, from heart attacks to revolutions. These claims should be viewed with skepticism until replicated by rigorous studies, as the history of science is littered with spurious correlations that failed to hold up under scrutiny. What we can say with confidence is that the sun's influence on Earth is pervasive and multifaceted. The obvious effects, light and heat, are so fundamental that we often take them for granted. The less obvious effects, from the solar wind shaping the magnetosphere, to ultraviolet radiation affecting atmospheric chemistry, to magnetic activity influencing technology, remind us that our star is not just a distant light in the sky, but an active participant in the environment we inhabit. Let us now look forward and consider what the future holds for our understanding of and relationship with the sun. The next few years will bring new tools for observing solar activity. Several space missions are currently operating or in development that will provide unprecedented views of our star. The Parker Solar Probe, launched in 2018, is making progressively closer approaches to the sun, flying through the outer atmosphere and making measurements that were impossible before. By the time its mission ends, it will have approached within a few million miles of the sun's surface, closer than any previous spacecraft. The Solar Orbiter, a joint mission between ESA and NASA, launched in 2020, is providing new perspectives on the sun, including the first close-up images of the sun's polar regions. Understanding what happens at the sun's poles is important for predicting its magnetic behavior, as the reversal of the solar magnetic field that occurs each solar cycle begins at the poles. On the ground, new observatories are coming online with capabilities far exceeding their predecessors. The Daniel K. Isue Inouye Solar Telescope in Hawaii, which began science operations recently, has a 4-meter mirror that makes it the largest solar telescope in the world. Its resolution allows scientists to see details on the sun's surface as small as 20 miles across, revealing structures in the solar atmosphere that were previously invisible. These new observational capabilities will feed improved computer models of solar behavior. Scientists are working toward the goal of being able to predict solar activity days or even weeks in advance, much as meteorologists can now forecast weather patterns. This is a difficult goal because the sun is a complex system with many interacting processes operating on different scales, but progress is being made. Improved forecasting will enable better protection of our technology and people. If we can know several days in advance that a major geomagnetic storm is coming, we can take more extensive protective measures than if we only have a few hours of warning. Satellite operators can prepare their spacecraft. Power grid operators can reconfigure their systems. Airlines can plan their routes to avoid high radiation areas. Even ordinary people can take steps to prepare for potential disruptions. At the same time, we need to work on making our infrastructure more resilient to the effects of space weather. This means designing and building systems that can withstand geomagnetically induced currents, or that can be quickly repaired if damaged. It means maintaining stockpiles of critical spare parts, particularly for large transformers that are difficult and time-consuming to manufacture. It means developing operational procedures that can minimize damage when a major storm occurs. Some of this work is already underway. Power companies in some regions have installed devices to monitor and mitigate geomagnetically induced currents. Governments have commissioned studies of the potential impacts of extreme space weather and developed plans for responding to such events. The insurance industry has begun to take space weather seriously as a potential source of large losses. But more needs to be done. The threat from space weather falls into a category of risks that humans find difficult to manage. Low probability, but high consequence events. We tend to focus on immediate visible threats while neglecting distant invisible ones. A solar superstorm will not be the subject of daily news coverage until after it happens. By then, it will be too late to prepare. There is also the question of expanding human presence in space. As we establish a more permanent presence on the Moon and eventually send humans to Mars, protection from solar activity becomes even more critical. Neither the Moon nor Mars has a global magnetic field like Earth's. The Moon has no atmosphere to provide additional shielding. Mars has a thin atmosphere that provides some protection, but far less than Earth's. Astronauts on the Moon during a major solar event would need to take shelter in shielded habitats. The radiation dose from a large solar particle event could be lethal to an unprotected person. Future lunar bases will need to incorporate radiation shelters, perhaps built into the lunar soil or using water tanks as shielding. The challenge is even greater for a crewed mission to Mars. The journey takes months, during which the spacecraft and its occupants are exposed to deep space radiation with no planetary shielding at all. A major solar event during the transit could deliver a dangerous radiation dose before astronauts could reach the relative safety of Mars. Spacecraft designers are working on shielding approaches, but every kilogram of shielding adds to the mass that must be launched from Earth, making missions more expensive and difficult. These challenges are not insurmountable, but they require us to take solar activity seriously as a factor in space exploration planning. The Sun has always been there, doing its thing, but now we are venturing into regions where its influence is more direct and more dangerous. As we approach the end of our exploration, let us return once more to the giant sunspot that started our journey. It sits there on the face of the Sun, a dark blemish against the brilliant surface, harboring enormous magnetic energy in its twisted field lines. Scientists continue to watch it, tracking its evolution, looking for signs of impending activity. Perhaps, as you listen to this, the sunspot has already produced its fireworks and faded away, or perhaps it is still there, still building towards some climactic release. The Sun does not operate on human schedules. It follows its own rhythms, heedless of our observations and our concerns. What we know is that the Sun will continue to have sunspots for as long as it remains a main sequence star, fusing hydrogen in its core. Some of those sunspots will be giants like the current one. Some of them will unleash their stored energy in spectacular flares and CMEs. Some of those CMEs will be aimed at Earth, and eventually, one of them will be powerful enough to cause serious disruption to our technological civilization. This is not a prediction of doom, but simply an acknowledgement of reality. The question is not whether such an event will happen, but when and how well we will be prepared. The scientists and engineers working on space weather forecasting and infrastructure hardening are racing against an uncertain deadline. They do not know how much time they have. None of us do. In the meantime, the sun remains our constant companion, the source of the light and warmth that make life possible. We wake each morning to its light. We mark our days and seasons by its position in the sky. We owe it everything, and yet we rarely think about it, so constant and reliable has it seemed throughout human history. The study of sunspots and solar activity reminds us that this reliability is not absolute. The sun is not unchanging. It has moods, cycles, tantrums. For billions of years, life on Earth has weathered these moods within the protective embrace of the atmosphere and magnetic field. Now, for the first time, we have extended our civilization beyond that protection, making ourselves vulnerable in new ways. This is not cause for despair. It is cause for wonder at what we have built and what we continue to learn. It is cause for prudent preparation, for taking seriously a threat that is real, even if it is not immediate. And it is cause for humility, for remembering that we are small creatures orbiting an ordinary star in a vast universe that operates on scales far beyond our everyday experience. The giant sunspot will do what it will do. We will watch and learn and prepare as best we can. And life will go on, as it has for billions of years, on this small world bathed in the light of a star that neither knows nor cares that we exist, yet without which we would not be here to wonder about it at all. The sun rises and sets, the seasons turn, and the solar cycle continues its ancient rhythm. Sunspots appear and fade, flares erupt and subside, CMEs race through the solar system. Occasionally, one of them hits Earth and reminds us of our connection to that distant nuclear furnace. Most of the time, we go about our lives, enjoying the warmth and light without giving it much thought. Perhaps that is as it should be. The sun has been reliable enough for all of human history. The chances of a catastrophic event in any given year are small. We have more immediate concerns to occupy our attention. But it does not hurt to look up occasionally, to appreciate the star that makes our existence possible, to remember that the universe is vast and powerful and indifferent to our plans. In that awareness lies wisdom, the wisdom to enjoy what we have while preparing for challenges to come, the wisdom to see ourselves as part of something much larger than our daily concerns, the wisdom to feel awe and gratitude for the cosmic good fortune that placed us here, on this planet, at this distance from this star, in conditions just right for life to flourish. The giant sunspot reminds us of all this. It is a momentary feature on the face of a star, something that will come and go in a few weeks, while the sun continues its billions of years of existence. But for a brief moment, it focuses our attention on the remarkable reality of our situation. We are creatures of a star, children of the sun in the most literal sense, made from atoms forged in stellar furnaces and nourished by energy generated in nuclear fires. Our fate is bound up with our star's fate, always has been, always will be. And so we watch the sunspot, this messenger from our star, carrying news of magnetic turmoil and stored energy. We watch and wonder and prepare as best we can for whatever it might bring. And we appreciate, perhaps more than we usually do, the constant companion that rises each morning to light our world. The sun is a wonder. Its dark spots and bright flares, its million-degree corona and billion-ton ejections, its ancient cycles and unpredictable outbursts, all of it is part of the ongoing story of a star in midlife, doing what stars do. We are privileged to observe it, to study it, to begin to understand it. We are challenged to adapt to its moods, to protect ourselves from its occasional violence, to thrive in its light while respecting its power. That is the situation we find ourselves in, watching a giant sunspot cross the face of our star, wondering what it will do, knowing that we cannot control it, but only observe and prepare. It is a situation that should inspire both humility and confidence. Humility at our smallness, in the face of cosmic forces, confidence in our ability to understand and adapt. The sun will continue to shine. The sunspots will continue to appear and disappear. Life will continue to flourish on this small world, adapting as it always has to the conditions provided by our star. And we, the latest chapter in Earth's long story of life, will continue to watch and wonder and reach for the stars, even as we remain forever dependent on the one star that matters most. As we draw our exploration to a close, let us reflect on what we have learned. We have journeyed from the surface of the sun, where magnetic field lines twist and erupt, to the depths of Earth's core, where flowing iron generates our protective magnetic shield. We have traced the path of energy from nuclear fusion in the sun's heart to the light that falls on our faces each day. We have considered the threats that solar activity poses to our technological civilization and the efforts underway to protect against them. Through it all, one theme has emerged: the profound interconnection between our star and our world. The sun is not just a light in the sky, but an active presence in our environment, shaping everything from the weather to the performance of our technology. We are not separate from the sun, but intimately connected to it, dependent on it for everything we value. This connection carries both risks and rewards. The risk is that a major solar event could disrupt our civilization in ways we can barely imagine. The reward is the light and warmth that make life possible, the energy that drives our weather systems and our economy, the beauty of a sunrise and the spectacle of an aurora. Understanding this connection is the first step toward managing it wisely. We cannot control the sun. We can only observe it, understand it, and adapt to what it does. That is the human story in a nutshell, adapting to the environment we find ourselves in, using our intelligence to thrive where other creatures could not. The giant sunspot is a reminder that this adaptation is an ongoing process, not a completed achievement. We have built a remarkable civilization, but it is vulnerable in ways we are only beginning to understand. The challenge for our generation is to recognize these vulnerabilities and address them before they become crises. This is not a task for scientists and engineers alone. It requires public awareness and political will. It requires individuals to understand the risks and support efforts to mitigate them. It requires businesses to consider space weather in their planning and investment. It requires governments to take the threat seriously and invest in research and infrastructure. The sun does not care about our politics or our priorities. It will continue doing what it has done for billions of years. The question is whether we will be ready when it next reaches out to touch our world with one of its magnetic tantrums. I believe we can be ready. I believe that the same intelligence and adaptability that has allowed humans to thrive in every environment on Earth can help us manage the challenges of living with an active star. It will not be easy, and there will be setbacks along the way, but we have the knowledge, the tools, and the capability to protect ourselves. What we need now is the will to act, to invest in forecasting and hardening, to prepare for an event that might not happen in our lifetimes, but certainly will happen eventually. This is the kind of long-term thinking that does not come naturally to humans, who are wired to focus on immediate threats. But it is essential if we want our technological civilization to endure. The giant sunspot will pass. The solar cycle will continue. New sunspots will appear, and eventually one of them will produce the major event we are preparing for. When that day comes, I hope we will look back on this moment as a time when we began to take the threat seriously and take the steps needed to protect ourselves. Until then, enjoy the sun, feel its warmth on your face, watch the sunrise and sunset. Know that you are connected to that distant star in ways both obvious and subtle, dependent on its energy for every breath you take and every thought you have. The sun is our star. Its story is our story. And its moods, including the giant sunspot we have been discussing, are part of the ongoing relationship between a star and the life it has made possible. Thank you for joining me on this journey from the churning surface of the sun to the depths of space to our own vulnerable planet. The universe is vast and full of wonders, and the nearest wonder of all is the star that rises each morning to light our world. May we learn to appreciate it, understand it, and live wisely in its light. The cosmos awaits, and there is always more to explore. The sun, with its dark spots and brilliant flares, its cycles and storms, is just one of countless stars in a galaxy of hundreds of billions. Each of those stars has its own story, its own planets perhaps, its own potential for life. But this star, our sun, is the one that matters to us. It is our home star, the center of our small corner of the universe. As we watch the giant sunspot evolve and eventually fade, we are witnessing a tiny chapter in the long story of a star in the prime of its life. Billions of years from now, the sun will exhaust its hydrogen fuel and begin to die, swelling into a red giant that will swallow the inner planets before shedding its outer layers and collapsing into a white dwarf. But that is far in the future, so far that it is almost meaningless on human timescales. For now, and for as long as humans exist, the sun will be our constant companion, source of light and life and occasionally danger. Understanding it, appreciating it, and preparing for its occasional tantrums is part of what it means to be an intelligent species living in orbit around an active star. The giant sunspot is a reminder of this reality. Look up at the sun, but safely, never directly, and know that you are seeing a star in all its complexity and power. Know that dark spots and bright flares are part of its nature, part of what makes it the dynamic living thing that has nurtured life on Earth for billions of years. And know that we are watching, scientists and citizens alike, keeping an eye on our star, ready to respond when it next reminds us of its awesome power. That is the relationship between humanity and the sun, a relationship of dependence and vulnerability and wonder, a relationship that will continue as long as we exist as a species. The sun will rise tomorrow, as it has every day of human history. The giant sunspot will do whatever physics dictates, and we will go on, living our lives in the light of a star that neither knows nor cares about us, yet without which none of us would be here to wonder about anything at all. This is the human condition, to be aware of our place in the cosmos, to understand something of the forces that shape our existence, to feel both small and significant at the same time. The giant sunspot, for all its size, is just a temporary blemish on the face of our star. But the questions it raises about our vulnerability, our preparedness, our relationship with the cosmos, These are questions that will matter as long as humans exist. Sleep well tonight, knowing that the sun will rise again tomorrow, that scientists are watching over our star, that life goes on despite the occasional cosmic storm. The universe is vast and sometimes violent, but it is also beautiful beyond description. The same sun that threatens our technology with its magnetic outbursts also paints the sky with glorious colors at dawn and dusk, powers the ecosystems that sustain us, and makes possible every moment of joy and wonder we experience. That is the duality of our star, giver of life and occasional threat, constant companion and unpredictable wildcard. Embracing this duality, understanding it, and adapting to it is part of what it means to be human in the 21st century. The giant sunspot will fade, new ones will appear, the great cycle will continue, and we will continue to watch, to wonder, and to prepare for whatever our star decides to do next. May the sun shine gently on your world, and may we all be ready when it does not. Rest well as the cosmos turns, knowing that you are part of something vast and ancient and ongoing. The story of the sun and earth is still being written, and you are here to witness a few chapters of it. That is a privilege beyond measure. The universe is speaking to us through sunspots and solar flares, through the aurora and the geomagnetic storms. It is telling us about the forces that shape our existence, the power that drives our star, the connection between events millions of miles away, and the functioning of our technology right here on Earth. Listen to what the universe is telling us. Learn from it, prepare for it, and then go on living, enjoying the warmth and light that make life possible, appreciating the cosmic good fortune that placed us here, on this world, orbiting this star, in this moment of cosmic history. The giant sunspot is a message from our star. What we do with that message is up to us, and with that, our journey comes to an end. The sun continues its ancient cycle, indifferent to our observations, but central to our existence. The giant sunspot tells its story of magnetic turmoil and stored energy. And we, small creatures on a small world, watch and wonder and prepare for whatever comes next. The cosmos awaits your dreams tonight. May they be filled with wonder at the vast universe we inhabit and gratitude for the star that makes our existence possible. Sleep well, and when you wake, look up at the sun, that familiar yet extraordinary sight, and remember what you have learned about its dark spots and brilliant heart. The sun is our star. Its story is our story. And tomorrow, as it has for billions of years, it will rise again to light our world. Good night, and may the gentle light of stars guide your sleep until morning comes again. But before you drift off, let us explore a few more wonders about our star and the remarkable dance it performs with our planet. There is still so much to discover, so much to appreciate about the relationship between the sun and Earth. Consider for a moment the journey that sunlight takes to reach your eyes. Deep in the core of the sun, where temperatures exceed 15 million degrees and pressures are crushing beyond imagination, hydrogen atoms are forced together with such violence that they fuse into helium. This process releases energy in the form of gamma-ray photons, packets of pure electromagnetic radiation. But these photons do not travel straight from the core to the surface. The sun's interior is so dense, so packed with matter, that a photon can only travel a tiny fraction of an inch before it collides with something. That collision absorbs the photon and then re-emits another one in a random direction. This process repeats over and over again, billions upon billions of times. The photon bounces around like a pinball in the densest pinball machine imaginable. Scientists estimate that it takes a photon somewhere between 10,000 and 170,000 years to random walk its way from the core to the surface. The exact number depends on the model and assumptions used, but the basic point is astounding. The light that falls on your face today began its journey inside the sun during the last ice age, or even earlier. It is ancient light by the time it reaches the surface. Once a photon finally makes it to the photosphere, the surface layer we can see, everything changes. The sun's atmosphere is transparent enough that the photon can finally travel in a straight line. It races across the 93 million miles of space between the sun and Earth in just 8 minutes and 20 seconds. After millennia of bouncing around inside the sun, the final leg of the journey is a sprint. And then that photon hits your eye, or a leaf, or the surface of the ocean, and delivers its energy. The ancient light from the sun's core, transformed through countless collisions from gamma rays to visible light, finally completes its journey. Every moment of every day, you are bathed in light that began as nuclear fire deep inside a star. Light that is both 8 minutes old and tens of thousands of years old at the same time. This perspective helps explain why the giant sunspot matters so much to scientists. When they observe the sunspot, they are seeing a region where something has gone differently, where magnetic fields have interrupted the normal flow of energy from below. The sunspot is cooler not because it lacks energy, but because that energy is being blocked, stored in magnetic form, rather than flowing upward as heat. Think about what this means. The twisted magnetic field lines in a sunspot contain energy that has been accumulating for days, weeks, or even longer. When those field lines finally snap and reconnect, releasing that stored energy as a solar flare, it is like a dam breaking. All the energy that should have been radiating away peacefully is instead released in a sudden, catastrophic burst. The violence of this release is hard to comprehend. A major solar flare can release the energy equivalent of billions of nuclear bombs in just a few minutes. The temperature in the flare region can spike to tens of millions of degrees, hotter than the core of the sun itself. Particles are accelerated to speeds approaching the speed of light. Radiation pours out across the entire electromagnetic spectrum, and all of this happens on the surface of a star 93 million miles away, visible from Earth only as a brightening in certain wavelengths of light. We watch from our safe distance, protected by space itself from the worst effects of these cosmic explosions. But our technology extends into that space, and our civilization depends on systems that are vulnerable to what our star can do. Let us explore more about what happens inside sunspots, because understanding the physics helps us appreciate both the beauty and the danger. A sunspot is not just a dark patch. It is a three-dimensional structure extending deep into the sun's interior. The strong magnetic field that creates the sunspot punches through the surface like a giant finger of magnetism reaching up from below. The field strength in a large sunspot can exceed 3,000 Gauss, thousands of times stronger than Earth's magnetic field. This intense magnetic field does two things that make sunspots appear dark. First, it suppresses convection. In the normal sun, hot plasma rises from below, delivers its heat to the surface, cools, and sinks back down. This constant churning brings fresh heat from the interior to the surface. But the strong magnetic field in a sunspot acts like a barrier, preventing this normal circulation. Without fresh hot plasma rising from below, the surface in that region cools down. Second, the magnetic field changes how energy radiates away. In normal solar plasma, energy moves relatively freely as radiation and convection. In the magnetized plasma of a sunspot, energy transport is more difficult. The field lines act as channels that restrict how heat can flow. This further reduces the temperature of the visible surface. The result is a region that might be almost 2,000 degrees cooler than the surrounding photosphere. That is still incredibly hot by earthly standards, around 7,000 degrees in the umbra, compared to nearly 10,000 in the normal photosphere. But the difference in temperature translates to a dramatic difference in brightness. The intensity of light emitted by a hot object goes as the fourth power of its temperature, so even a relatively modest temperature difference produces a much larger brightness difference. When we look at a sunspot, we are seeing a window into the interior of the sun, a place where the magnetic field has created conditions different from the norm. Through that window, we can learn about the magnetic processes that drive so much of solar activity. The magnetic field in a sunspot does not stay constant. It evolves over time, shaped by the constant churning of the sun's plasma. New magnetic flux can emerge from below, adding to the complexity of the field. Existing field lines can be stretched and twisted by the differential rotation of the sun. Opposite polarities can be pushed together, building up stress that will eventually be released. Scientists use specialized instruments called magnetographs to measure the magnetic field strength and orientation across the sun's surface. These observations reveal the intricate structure of sunspot magnetic fields, showing how different polarities interact and evolve. By tracking these changes over time, researchers try to identify the conditions that precede major flares and CMEs. This is where the challenge lies. The sun's magnetic field is incredibly complex, with structures spanning a huge range of scales. Large-scale patterns in the global magnetic field set the stage for activity, but the actual triggers for flares occur at scales so small they are difficult to observe. A flare might be triggered by the interaction of field lines in a region just a few hundred miles across, on a star that is 864,000 miles in diameter. Predicting exactly when and where a flare will occur is like predicting exactly when a stressed piece of glass will shatter. We can identify conditions that make shattering likely. We can watch for warning signs. But the actual moment of failure depends on microscopic details that are hard to observe and impossible to predict precisely. This uncertainty does not mean forecasting is useless. Scientists can identify sunspots with high flare potential and issue watches and warnings when conditions are favorable for major activity. They just cannot say exactly when, or even if, a particular sunspot will produce the big one. It is probabilistic forecasting, similar to how weather forecasters might say, there is a 70% chance of thunderstorms without being able to say exactly when and where lightning will strike. The giant sunspot we have been discussing falls into the category of high potential. Its size, its magnetic complexity, its position in the current solar cycle, all of these factors suggest it could produce significant activity. Whether it actually will depends on the microscopic evolution of its magnetic field, something we can observe but not control or fully predict. Let us now consider what happens after a flare erupts and a CME is launched toward Earth. The chain of events that follows is both fascinating and consequential. When a major flare occurs, the first thing that reaches Earth is the electromagnetic radiation, light in all its forms from radio waves to gamma rays. This travels at the speed of light and arrives in just over 8 minutes. The most immediate effects are on the ionosphere. the layer of charged particles high in Earth's atmosphere. The sudden increase in X-ray and extreme ultraviolet radiation from the flare dramatically increases the ionization of the upper atmosphere. More atoms are stripped of their electrons, creating a denser, more electrically conductive layer. This can have significant effects on radio communications. High-frequency radio signals normally bounce off the ionosphere, allowing them to travel beyond the horizon. But when the ionosphere is disturbed by a solar flare, it can absorb these signals instead of reflecting them. Radio operators on the sunlit side of Earth suddenly find that their long-distance communications have gone dead. This is called a radio blackout, and it can last for minutes to hours depending on the intensity of the flare. Airlines and ships that depend on high-frequency radio for communication over the ocean can be significantly affected. Modern aircraft have satellite communications as a backup, but the loss of HF radio is still a problem. Emergency services that rely on these frequencies can also be disrupted. The radiation also affects the global positioning system. GPS signals pass through the ionosphere on their way from satellites to receivers on the ground. The disturbed ionosphere during a flare can bend and delay these signals in unpredictable ways, introducing errors in position determination. For most consumer GPS use, this is a minor inconvenience, but for precision applications like aircraft landing systems or surveying, the errors can be significant. Meanwhile, high-energy particles accelerated by the flare are racing toward Earth at speeds approaching the speed of light. These solar energetic particles can arrive within minutes to hours of the flare, much faster than the CME itself. They pose a radiation hazard to astronauts and can damage satellite electronics. The most energetic of these particles can penetrate deep into Earth's atmosphere, reaching aircraft altitudes and even the surface. At high altitudes, they can cause avionics disruptions, single event upsets, where a high-energy particle flips a bit in a computer memory or logic circuit. This is why critical aircraft systems have redundancy and error correction to handle occasional bit flips from cosmic rays and solar particles. At the surface, the radiation increase is much smaller, shielded by the bulk of the atmosphere above. But it is measurable, particularly at high latitudes where Earth's magnetic field provides less protection. Radiation monitors on the ground can detect the increase in particle flux during major solar events. Then comes the coronal mass ejection, the billion-ton cloud of solar plasma and magnetic field heading toward Earth. It travels much slower than light, typically taking 1 to 4 days to cross the distance from the Sun to Earth. During this time, scientists track its progress using spacecraft positioned between the Sun and Earth. The primary watchdog is the DS-COVA satellite, positioned at the first Lagrange point, about 1 million miles from Earth toward the Sun. From this vantage point, DS-COVA can sample the solar wind and any incoming CMEs before they reach our planet. It provides about 15 to 60 minutes of warning before a CME arrives at Earth. Enough time to take final protective actions, but not enough for major preparations. When the CME finally arrives, it collides with Earth's magnetosphere at speeds that can exceed 1 million miles per hour. The shock of impact compresses the magnetosphere on the day side, pushing the boundary between solar wind and magnetosphere closer to Earth. This compression can push the magnetopores inside the orbit of geosynchronous satellites, exposing them directly to the solar wind plasma. The interaction between the CME and the magnetosphere depends critically on the orientation of the magnetic field embedded in the CME. This field was originally part of the Sun's magnetic field, carried along frozen into the expanding plasma. If this field happens to be oriented southward, opposite to Earth's northward pointing field at the equator, the two fields can connect through magnetic reconnection. When reconnection happens, it opens a pathway for energy and particles from the CME to enter the magnetosphere. The magnetosphere becomes coupled to the CME, absorbing energy from the solar wind at a tremendous rate. This energy goes into accelerating particles, driving electric currents in the ionosphere and heating the upper atmosphere. The result is a geomagnetic storm, a period of intense activity in Earth's magnetic environment. The storm can last for hours to days, depending on the size and speed of the CME and how long the magnetic field remains favorably oriented for reconnection. During a major geomagnetic storm, the aurora expands dramatically from its usual position near the poles. Under normal conditions, the aurora is confined to a ring around 65 to 70 degrees latitude, visible mainly from places like Alaska, Scandinavia, and Antarctica. During a major storm, the auroral zone can expand down to 50 degrees latitude or even lower, bringing the northern lights to places like the northern United States and Central Europe. The strongest storms have produced auroras visible from locations as far south as Mexico, the Caribbean, and Hawaii. During the Carrington event of 1859, the aurora was reportedly visible from Colombia, just a few degrees north of the equator. Imagine looking up at the sky from a tropical location and seeing curtains of green and red light dancing overhead, a sight normally reserved for polar regions. The beauty of the expanded aurora is matched by the disruption happening on the ground and in space. Electric currents surge through the ionosphere, following paths determined by the geometry of the geomagnetic storm. These currents induce corresponding currents in any long conductor on the surface. The geomagnetically induced currents that threaten power grids and pipelines. Satellites experience increased drag as the upper atmosphere heats and expands during the storm. This heating occurs because energy from the CME is being deposited in the thermosphere, hundreds of miles above the surface. The increased temperature causes the atmosphere to expand upward, putting more particles at the altitudes where satellites orbit. The increased drag can cause satellites to lose altitude faster than expected, requiring extra fuel to maintain their orbits. The disturbed magnetic environment also makes navigation more difficult. Compass needles may wander as the local magnetic field fluctuates. GPS accuracy degrades as the disturbed ionosphere introduces unpredictable delays in satellite signals. For precision applications, these errors can be significant. Eventually, the storm subsides as the CME passes and the magnetosphere recovers its normal configuration. The aurora retreats toward the poles. The induced currents fade. Life returns to normal, at least until the next event. But the memory of the storm lingers, in satellite data degraded during the event, in transformer wear from induced currents, in scientific papers analyzing what happened. Each storm adds to our understanding of how the Sun and Earth interact, helping us prepare for future events. Now let us consider the human element in all of this. The scientists and engineers who monitor the Sun and its effects on Earth have developed into a dedicated community over the decades, united by their fascination with space weather and their sense of responsibility to protect society from its effects. Space weather forecasters work around the clock at prediction centers operated by national agencies like NOAA in the United States, ESA in Europe, and similar organizations in other countries. They monitor a constant stream of data from solar observatories on the ground and in space. watching for signs of activity that could affect Earth. When a major event occurs, these forecasters must quickly analyze the situation and issue warnings to affected sectors. Satellite operators need to know if they should put their spacecraft into safe mode. Power grid operators need to know if they should prepare for geomagnetically induced currents. Airlines need to know if polar routes should be avoided due to increased radiation. The decisions these forecasters make can have significant economic consequences. A false alarm that causes unnecessary protective actions costs money and disrupts operations. A missed warning that allows a solar event to catch people unprepared can cost even more. The forecasters must balance these competing pressures, issuing warnings when the risk is significant, while avoiding crying wolf too often. The tools available to forecasters have improved dramatically in recent decades. Better observations of the Sun, improved models of CME propagation through space, enhanced monitoring of the solar wind, all of these contribute to more accurate forecasts. But space weather remains inherently difficult to predict, and surprises are always possible. The forecasters work in a strange kind of tension, hoping for quiet on the Sun so that society is not disrupted, yet also fascinated by the physics of solar activity and professionally interested in observing and studying major events. When a really big sunspot appears, there is a mixture of concern and excitement in the community. Will this be the one? Will it produce a major event? What will we learn from it? The current giant sunspot has generated exactly this kind of reaction. Scientists are watching it carefully, tracking its evolution day by day, ready to issue warnings if it shows signs of producing a major flare or CME. At the same time, they are learning from it, gathering data that will improve their understanding and eventually their forecasts. This is how science progresses, one observation at a time, one event at a time, building knowledge that will benefit future generations. The scientists watching the sunspot today are part of a long tradition stretching back to Galileo and the first telescope observers of sunspots. They stand on the shoulders of countless predecessors who dedicated their careers to understanding our star. And now let us return one final time to the question that has guided our exploration. Can this giant sunspot end life on Earth? We have established that the answer is no, in the most literal sense. Life itself, the microbes in the soil, the fish in the sea, the birds in the sky, none of these will be directly killed by a solar event. Earth's atmosphere and magnetic field provide enough protection that even the most extreme solar activity will not cause biological extinction. But we have also established that a major solar event could end our way of life, at least temporarily. The technological infrastructure that modern civilization depends on is vulnerable to space weather in ways that would have been unimaginable to previous generations. A Carrington-class event could potentially knock out power grids across large portions of the planet, disable satellites, disrupt communications, and trigger an economic and social crisis. The giant sunspot currently on the Sun is capable of producing such an event. Whether it actually will depends on factors we cannot fully predict. The Sun is following its own physics, indifferent to our concerns. What we can do is prepare. We can continue to improve our forecasting capabilities. We can harden our infrastructure against geomagnetically induced currents. We can develop operational procedures to minimize damage when a major storm occurs. We can educate the public and policymakers about the reality of space weather threats. These preparations are not glamorous. They do not generate headlines or excite public attention. But they are essential if our technological Civilization is to endure and thrive in the long term. The sun will continue to have giant sunspots and produce major flares and CMEs. That is part of what it means to be a main sequence star. Our job is to adapt, to learn to live with the sun's moods while continuing to enjoy its benefits. This is the human story writ large. We are a species that has learned to adapt to every environment on Earth, from frozen tundra to scorching desert, from sea level to high mountains. Now we are learning to adapt to the space environment, to the radiation and magnetic fields and solar winds that fill the solar system. It is the latest chapter in a long story of adaptation and resilience. The giant sunspot will fade eventually, as all sunspots do. The magnetic field that created it will disperse back into the solar interior. The sun will continue its 11-year cycle, building toward maximum and then declining toward minimum. New sunspots will appear, some large and some small, some quiet and some explosive. And we will continue to watch. Scientists will continue to monitor the sun with ever-improving instruments. Forecasters will continue to issue warnings when conditions warrant. Engineers will continue to design more resilient systems. Society will continue to function, most of the time unaware of the distant star that makes it all possible, occasionally reminded by a particularly dramatic event. That is the equilibrium we have reached, a technological civilization living in the light of an active star, vulnerable to its tantrums, yet remarkably adaptive and resilient. The giant sunspot is a test of that equilibrium, a reminder that we have not yet mastered all the challenges of our cosmic environment. May we rise to meet this challenge as we have met so many others. May we learn from the sunspot and prepare for future events. May we continue to explore the universe with curiosity and wonder, knowing that there is always more to discover. The sun will rise tomorrow, carrying its dark spots and bright flares across the sky. Life will go on in all its diversity and beauty on this small world orbiting an ordinary star. And we will be here, watching and wondering, grateful for the light that makes everything possible. Sleep now and let the cosmos turn as it always has. The sunspot keeps its secrets for another day, and the universe continues its ancient dance of energy and matter, space and time. You are part of that dance, a brief spark of consciousness in an incomprehensibly vast universe, yet connected to everything through the light of stars. Dream of distant suns and swirling galaxies. Dream of auroras dancing across polar skies. Dream of the great sunspot, dark against the brilliant surface of our star, holding its store of magnetic energy, waiting to release it or fade peacefully away. Tomorrow, the journey continues. Tonight, rest. The universe is vast, and there is always more to explore. But the greatest wonder of all may be the star that rises each morning, the familiar yet extraordinary sun that has watched over life on Earth for billions of years. It is our star, our constant companion, our source of light and life and occasional danger. Appreciate it, understand it, prepare for its moods, and then go on living in the warmth and light that make existence possible on this small world we call home. The giant sunspot waits on the face of the sun. What happens next is up to the physics of plasma and magnetism, forces far beyond our control. But how we respond, how we prepare, how we adapt, that is up to us. May we choose wisely. May we act thoughtfully. May we thrive in the light of our star for generations to come. And may you sleep peacefully tonight, dreaming of the wonders of the universe, knowing that tomorrow the sun will rise again. Let us linger a while longer in the gentle darkness, contemplating a few more aspects of our remarkable star that deserve attention. The night is long, and there is still so much to appreciate about the sun that illuminates our days. Consider the sheer age of our star and the journey it has taken to reach this point. The sun formed approximately 4.5 billion years ago from a vast cloud of gas and dust floating in the Milky Way galaxy. That cloud was not pure hydrogen and helium, the original elements created in the Big Bang. It was enriched with heavier elements, carbon and oxygen, iron and gold, elements forged in the hearts of earlier stars that had lived and died long before our sun was born. When those ancient stars exploded as supernovae, they scattered these heavy elements into space. Slowly, over millions of years, gravity began to pull the enriched gas cloud together. As it collapsed, it began to rotate faster and faster, like a figure skater pulling in their arms. Most of the material fell toward the center, where temperatures and pressures built, until nuclear fusion ignited. The sun was born. Around the newborn star, leftover material formed a disk of gas and dust. Within this disk, small particles began sticking together, building larger and larger objects over millions of years. Eventually, planets formed, including our own Earth. Every atom in your body except for hydrogen was forged inside a star, either in the ancient stars whose deaths enriched our cosmic nursery, or in our sun itself through nuclear reactions in its core. When you look at the sun, you are looking at your own distant origin. You are made of star stuff, as the astronomer Carl Sagan famously said. The calcium in your bones, the iron in your blood, the carbon in your cells, all of it was created by stellar processes billions of years ago. The light falling on your face is generated by the same nuclear fires that created the elements of which you are made. This connection between the sun and life runs even deeper. For billions of years, the sun's energy has been the driving force behind almost all life on Earth. Plants capture sunlight through photosynthesis, converting solar energy into chemical energy stored in sugars and other organic molecules. Animals eat plants or eat other animals that eat plants, transferring that stored solar energy through the food chain. Every bite of food you take is, at its core, stored sunlight. The fossil fuels that power much of our civilization are also stored sunlight. Coal is the remains of ancient plants that captured solar energy millions of years ago. Oil and natural gas formed from the remains of tiny marine organisms that lived in ancient seas, fed ultimately by the sun's light. When we burn these fuels, we are releasing energy that the sun provided to Earth hundreds of millions of years before humans existed. Even the weather is driven by solar energy. The sun heats the equator more than the poles, creating temperature differences that drive atmospheric circulation. Warm air rises at the equator and flows toward the poles, while cold polar air sinks and flows toward the equator. This circulation pattern, modified by Earth's rotation and the distribution of land and sea, creates the weather systems that bring us rain and wind, snow and sunshine. The water cycle depends on solar energy. The sun's heat evaporates water from the oceans and land surfaces. That water vapor rises into the atmosphere, forms clouds, and eventually falls back to Earth as precipitation. Rivers carry the water back to the sea, completing the cycle. Without the sun's heat to drive evaporation, the water cycle would stop, and life as we know it would be impossible. Even the seasons are a gift from the sun, combined with Earth's tilted axis. As Earth orbits the sun each year, different hemispheres are tilted toward or away from our star, receiving more or less direct sunlight. This variation in solar heating creates the cycle of spring, summer, fall, and winter that organizes so much of life on Earth, from the blooming of flowers to the migration of birds. All of this happens because we orbit a star at just the right distance, in a zone that astronomers call the habitable zone, or Goldilocks zone. Not too hot, not too cold, but just right for liquid water to exist on the surface. Liquid water is essential for life as we know it, and the sun's energy maintains the temperature that allows it to persist. This fortuitous positioning is not guaranteed. If Earth were a bit closer to the sun, temperatures might be too high for liquid water to exist. The oceans would evaporate, water vapor would trap even more heat, and our planet might end up like Venus, a hellish world, with surface temperatures hot enough to melt lead. If Earth were a bit farther out, temperatures might be too low. Water would freeze, ice would reflect more sunlight back to space, cooling the planet further, and Earth might end up like Mars, a frozen desert. Instead, by cosmic good fortune, Earth orbits in the narrow band where temperatures are just right. The sun provides exactly the amount of energy we need, and our atmosphere regulates that energy through the greenhouse effect, keeping temperatures comfortable for life. This delicate balance has persisted for billions of years, allowing life to evolve from simple single-celled organisms to the complex biosphere we see today. But this balance is not static. The sun has been gradually getting brighter over its lifetime. When the sun first ignited 4.5 billion years ago, it was about 30% dimmer than it is today. If that dim sun shone on modern Earth, our planet would freeze solid. Yet geological evidence tells us that liquid water existed on Earth even in those early days. This is known as the faint young sun paradox. Scientists think the early Earth was kept warm by a stronger greenhouse effect than we have today. Higher levels of carbon dioxide and possibly other greenhouse gases in the ancient atmosphere trapped more of the sun's weaker energy, maintaining temperatures suitable for liquid water. Over billions of years, as the sun gradually brightened, Earth's greenhouse effect weakened, maintaining a rough equilibrium. This long-term adjustment is managed not by any conscious process, but by geological and biological feedback loops. Volcanic eruptions release carbon dioxide into the atmosphere. Weathering of rocks removes carbon dioxide. Plants absorb carbon dioxide through photosynthesis. When conditions change, these processes adjust over millions of years, keeping Earth's climate within the bounds suitable for life. Understanding this long-term relationship between the Sun and Earth gives perspective on the shorter-term variations we have been discussing. The 11-year solar cycle, with its waxing and waning sunspots, is a tiny fluctuation compared to the slow brightening of the Sun over billions of years. The giant sunspot currently concerning scientists is an even tinier blip, a momentary feature on a star that has been shining for eons and will continue shining for billions of years more. Yet these small fluctuations matter to us because of our short timescales. A geomagnetic storm that disrupts power grids for a few days can have enormous economic and social impacts. A solar event that damages satellites can set back space programs by years and cost billions of dollars. The sun operates on cosmic timescales, but we live on human timescales, and even brief solar hiccups can be consequential for us. This mismatch of timescales is worth contemplating. From the sun's perspective, if the sun could have a perspective, the entire history of human civilization is less than an eye blink. The pyramids were built, the Roman Empire rose and fell, the Industrial Revolution transformed the world, and the digital age dawned, all in a span so brief that the sun has barely changed. The giant sunspot will come and go without the sun noticing or caring. From our perspective, the sun is the most constant thing in our lives. It has risen every morning of every day of our lives and will continue to do so for as long as we and our descendants exist. We count our years by Earth's orbit around the sun and our days by Earth's rotation in sunlight. The sun is the metronome of our existence. Yet we are now beginning to understand that this constant companion has moods and cycles, that its surface roils with magnetic activity, that it occasionally throws tantrums that can affect our technology thousands of miles away. We are like children, beginning to see our parent as a complex being with a life beyond our understanding, rather than simply a constant presence meeting our needs. This maturation of our relationship with the sun is one of the great intellectual achievements of recent centuries. From worshipping the sun as a god, to understanding it as a nuclear furnace, to monitoring its magnetic activity in real time, we have come an enormous distance. Each step has revealed new wonders and new challenges, new reasons for awe and new reasons for caution. The giant sunspot is part of this ongoing journey of discovery. When scientists observe it, they are not just tracking a potential threat. They are studying the physics of plasma and magnetism, learning how stars behave, gathering data that will improve our understanding for generations to come. Science is a conversation across time, and the scientists of today are speaking to the scientists of tomorrow through the observations they make and the papers they publish. Let us now consider a few more examples of how solar activity has affected human history, beyond the Carrington event we discussed earlier. In May 1921, a geomagnetic storm struck that was nearly as powerful as the Carrington event. Telegraph systems were again disrupted, with equipment catching fire and operators receiving shocks. But by 1921, the world had a new technology that was even more vulnerable: the telephone system. The storm caused havoc with telephone networks across North America and Europe. Switching equipment was damaged and service was disrupted for hours. The 1921 storm also affected the growing electric power industry. In Sweden, a major power station caught fire. Railroad signaling systems, which depended on electric circuits running along the tracks, were disrupted. A similar storm today, with our much more extensive and interconnected electrical infrastructure, would cause far greater damage. In August 1972, during the Apollo era, a major solar event occurred that could have been catastrophic for astronauts. Fortunately, the event happened between Apollo missions, when no one was in deep space. But studies later showed that astronauts caught in lunar transit or on the lunar surface during such an event could have received radiation doses high enough to cause acute radiation sickness or even death. This near miss highlighted the importance of solar forecasting for crewed spaceflight. Today, space agencies carefully monitor solar activity when astronauts are outside the protective cocoon of Earth's magnetosphere. The space shuttle, which orbited entirely within the magnetosphere, was relatively protected, but the International Space Station, which orbits at a high enough altitude that some solar events can pose radiation risks, has procedures in place for astronauts to take shelter during major storms. Future missions to the Moon and Mars will face even greater challenges. The Moon has no magnetic field or atmosphere to provide protection. Mars has a thin atmosphere and only remnant, localized magnetic fields. Astronauts on the lunar surface or traveling through deep space to Mars will need either heavy radiation shielding, which adds mass and cost to missions, or the ability to shelter during major solar events, which requires accurate forecasting. This is one reason why space agencies are investing heavily in better solar monitoring and forecasting capabilities. The lives of astronauts may depend on our ability to predict when the sun will erupt. As humanity expands its presence in space, understanding and forecasting solar activity becomes not just an academic exercise, but a matter of life and death. Back on Earth, there have been several notable solar events in more recent decades that demonstrated our vulnerability. In March 1989, as we mentioned earlier, a major geomagnetic storm caused the collapse of the Hydro-Quebec power grid in Canada. The entire grid went down in 90 seconds as protective systems tripped one after another. 6 million people lost power for up to 9 hours in the middle of winter. The economic cost was estimated in the billions of dollars. This event was a wake-up call for power companies and governments. It demonstrated that our electrical infrastructure was vulnerable to space weather in ways that had not been fully appreciated. In the years since, significant efforts have been made to understand and mitigate this vulnerability, but the grid has also become more complex and interconnected, potentially increasing the damage that a major event could cause. In October 2003, a series of powerful solar storms known as the Halloween storms affected Earth over several days. These storms produced spectacular auroras visible from much lower latitudes than usual. They also caused problems for satellites, disrupted radio communications, and forced airlines to reroute polar flights. Power grid operators in North America took precautionary measures to prevent damage to transformers. The storms provided a real-world test of the procedures and preparations that had been developed since the 1989 event. Perhaps the most dramatic near-miss came in July 2012, when a massive CME erupted from the Sun with characteristics similar to the Carrington event. Fortunately, the eruption occurred on a part of the Sun that was not facing Earth. The CME shot off into space in a different direction, missing our planet entirely. We learned about the event only because the stereo spacecraft, positioned in an orbit that gave it a view of that region, detected the CME as it passed. Analysis of the 2012 event suggested it would have been comparable to, or possibly even more powerful than the Carrington event if it had hit Earth. The estimated economic damage from such a hit, given our current infrastructure, ranges from $1 to $2 trillion, with recovery potentially taking years rather than days. We dodged a bullet that we never even saw coming until after it had passed. These examples illustrate both the reality of the threat and the element of luck in our continued prosperity. Major solar events have occurred throughout history and will continue to occur. The question is not whether another Carrington-class event will happen, but when. And when it does, the consequences will depend heavily on how well we have prepared. As the night deepens and sleep approaches, let us turn our thoughts to a more philosophical contemplation of our place in the cosmos. We live on a small rocky world orbiting an ordinary yellow dwarf star in a suburb of a spiral galaxy containing hundreds of billions of other stars. The vastness of space is difficult to comprehend. Light from the sun takes 8 minutes to reach us. Light from the nearest other star takes more than 4 years. Light from the center of our galaxy takes about 26,000 years. And our galaxy is just one of hundreds of billions of galaxies in the observable universe. In this immensity, the relationship between Earth and the Sun seems almost intimate. A mere 93 million miles separate us from our star, a distance that light crosses in minutes. In cosmic terms, We are practically touching the sun. We are bathed in its light, warmed by its heat, shaped by its gravity, affected by its magnetic moods. Our world is the sun's world. This intimacy carries both comfort and vulnerability. The sun is reliable in ways that few things in the universe are. It has been shining steadily for 4.5 billion years and will continue for billions more. Empires rise and fall, mountains erode to dust, species evolve and go extinct, but the sun keeps shining. That constancy is the foundation on which all earthly life rests. But the sun is also powerful beyond our comprehension. The energy it releases every second exceeds the total energy human civilization has used in all of history. A single solar flare can release more energy than all the nuclear weapons ever built. A coronal mass ejection can carry 1 billion tons of plasma at millions of miles per hour. When the sun acts up, we are reminded that our reliable companion is also a force of nature on a scale we can barely imagine. The giant sunspot embodies this duality. It is a reminder of the sun's power and unpredictability. But it is also an opportunity for wonder, a window into the magnetic processes that drive our star. Through it, we can glimpse the dynamic nature of a stellar surface, the churning plasma and tangled field lines, the barely contained violence of a star in midlife. This sense of wonder is important. It is what drives scientists to spend their careers studying the sun, what motivates engineers to build better instruments and protective systems, what inspires writers and artists to contemplate our place in the cosmos. Wonder is the beginning of wisdom, and the sun offers abundant material for wonder. Yet wonder alone is not enough. We must also act on what we learn. The knowledge that major solar events can disrupt our technology is useless if we do not use that knowledge to prepare. The predictions that such events will eventually occur must translate into investments in resilient infrastructure. The warnings that scientists issue when dangerous sunspots appear must be heeded by those in positions to protect vulnerable systems. This is the challenge of our age, to combine wonder at the cosmos with practical action to thrive within it. We are the first species on Earth with the knowledge to understand the threats we face from space weather. We are also the first species with the capability to do something about those threats. Whether we rise to that capability is a test of our wisdom and foresight. The giant sunspot will pass, as all sunspots do. But the questions it raises will remain. How prepared are we for the inevitable major solar event? What more should we be doing to protect our civilization? How do we balance the costs of preparation against the risks of inaction? These are questions for policymakers, engineers, scientists, and citizens alike. They are questions that deserve serious attention, even when the sun is quiet and the threat seems distant, because the sun will not always be quiet. Someday, perhaps soon, perhaps not for decades, a giant sunspot will unleash its stored energy directly at Earth. When that day comes, we will either be ready or we will not. Let us hope we choose to be ready. Let us hope we use the time we have to strengthen our defenses, improve our forecasting, and build the resilient civilization that can weather any solar storm. The sun has given us everything. The least we can do is take its occasional tantrum seriously. As your thoughts grow soft and sleep beckons, carry with you the image of the sun, that blazing sphere that has watched over Earth for billions of years. Think of the giant sunspot, dark against the brilliant surface, holding its store of magnetic energy. Think of the scientists watching it, the engineers preparing for its potential outbursts, the vast network of spacecraft and ground stations monitoring our star around the clock. We are connected to the sun in ways both obvious and subtle. Its light wakes us each morning. Its heat warms our world. Its energy powers our lives. And its magnetic moods can disrupt the technology we have come to depend on. This is the cosmic context of human existence, a context we are only beginning to fully appreciate. The night sky above you is full of stars, each one a sun to whatever worlds might orbit it. Some of those stars have planets, perhaps even planets with life. If intelligent beings exist on those distant worlds, they too must grapple with the moods of their stars. They too must learn to thrive in the light of unpredictable suns. We are not alone in this challenge, even if we cannot yet communicate with our cosmic neighbors. For now, we have each other. Humanity is a single species on a single world, united by our dependence on a single star. The challenges we face from solar activity are shared challenges, requiring cooperation across national boundaries and cultural divides. The sun does not care about our politics. Its flares and CMEs affect the whole planet, regardless of who lives where. In confronting the sun, we are reminded of our common humanity. This is perhaps the deepest lesson of the giant sunspot. It is not just a scientific curiosity or a potential threat. It is a reminder that we are all in this together, sharing a small world orbiting a common star, facing challenges that require collective wisdom and action. If the sun can teach us that lesson, then even its tantrums serve a purpose. Rest now. Let the worries of the day fade as sleep approaches. The sun will rise tomorrow, as it has every day of your life. The giant sunspot will do what physics dictates, and scientists will watch and warn as needed. Life will go on, in all its beauty and complexity, on this remarkable world we call home. The cosmos is vast and ancient, and we are small and brief, but we are here, aware and wondering, capable of understanding and adapting. That is no small thing. In a universe of blind forces and mindless processes, we are the eyes through which the cosmos sees itself, the minds through which it knows itself. The sunspot that threatens our technology is also the sunspot we study and marvel at. Both responses, the caution and the wonder, are part of what it means to be human. Sleep well and dream of distant suns and swirling galaxies, of auroras dancing across polar skies, of the great ongoing story of energy and matter, stars and planets, life and mind. You are part of that story, a brief but precious chapter in a tale that spans billions of years. Tomorrow brings another day in the light of our star. Tonight, rest in the gentle darkness, knowing that you are cradled by a universe far vaster and more wonderful than we can ever fully comprehend. The sun awaits the dawn, and so do you. But before sleep takes you completely, let us spend a few more peaceful moments exploring the quieter mysteries of our star. There is beauty in the sun that goes beyond its power and danger, a beauty that has inspired poets and philosophers throughout human history. Ancient civilizations understood something fundamental about the sun, even without knowing the physics. They recognized that without it, nothing would exist. The Egyptians worshipped Ra, the sun god who sailed across the sky each day in a celestial boat. The Greeks told stories of Helios driving his golden chariot from east to west. The Aztecs built pyramids aligned to the movements of the sun and offered sacrifices to ensure it would continue to rise. These myths, whatever their factual limitations, captured an essential truth. We are children of the sun, utterly dependent on its light and warmth. Modern science has not diminished this truth. If anything, it has deepened it. We now know that the sun is not just a light in the sky, but a nuclear furnace whose fires have burned for billions of years. We know that every living thing on Earth is connected to the sun through chains of energy that stretch back to the first photosynthetic organisms. We know that the atoms in our bodies were forged in stellar furnaces, making us quite literally star stuff. This scientific understanding adds layers of meaning to the ancient sense of solar dependence. When we look at the sun, we are looking at the source of all earthly life, the origin of the atoms that make us up, the engine that drives weather and climate, the timekeeper that marks our days and seasons. No wonder ancient peoples worshipped it. The only surprise is that modern people take it so, for granted. The giant sunspot invites us to remember what we usually forget, that the sun is a living, dynamic thing, not just a constant background to our busy lives. It has cycles and moods, periods of activity and quiet. It evolves over time, gradually brightening as it ages. It will eventually die, billions of years from now, expanding into a red giant before collapsing into a white dwarf. The sun that seems so eternal to us is, on cosmic timescales, as mortal as we are. This shared mortality connects us to our star in an unexpected way. We are both part of the great cosmic cycle of birth, life, and death that governs everything in the universe. Stars are born, live their lives, and die. Planets form, support life for a time, and eventually become uninhabitable. Species arise, flourish, and go extinct. Individuals are born, live their brief lives, and pass away. At every scale, the same pattern repeats: emergence, existence ending. Knowing this does not diminish the value of existence. If anything, it enhances it. Every moment is precious because moments are finite. Every sunrise is a gift because there will not be infinite sunrises. The giant sunspot, threatening though it may be, is part of the great drama of cosmic existence, a drama we are privileged to witness and participate in. Consider the privilege of being alive at this moment in cosmic history. The universe is nearly 14 billion years old. For most of that time, there was no one around to appreciate its wonders. Stars burned and exploded, galaxies formed and merged, planets coalesced from cosmic dust, all without any conscious witness. Then, on a small rocky world orbiting an unremarkable star, life emerged and eventually evolved into beings capable of understanding the cosmos they inhabit. We are those beings. We are the universe becoming aware of itself. When we study the sun and its sunspots, we are the cosmos examining one of its own stars. When we contemplate the dangers of solar activity, we are matter and energy pondering their own behavior. This is extraordinary, almost miraculous, regardless of whether you frame it in religious or secular terms. The giant sunspot is part of this awakening. It is one more piece of the cosmic puzzle that we are assembling, one more chapter in the story we are learning to read. Every observation adds to our understanding. Every event, threatening or benign, teaches us something about how the universe works. We are students of the cosmos, and the sun is one of our most important teachers. As you drift towards sleep, let this perspective settle over you like a warm blanket. You are part of something vast and ancient, a cosmic story that began long before you and will continue long after. The worries of daily life, important though they may be, are set against a backdrop of immense scale and deep time. The giant sunspot, for all its potential danger, is just one small event in a universe filled with events beyond counting. This does not mean our concerns are trivial. Quite the opposite. Because we are the universe becoming conscious, our choices matter. What we do with our brief existence echoes through time, in ways we cannot always see. The scientists studying the sunspot are adding to human knowledge that will benefit future generations. The engineers preparing our infrastructure are protecting a civilization that may endure for millennia. Even ordinary people, going about their ordinary lives, contribute to the great human project of understanding and thriving in a cosmos that does not owe us anything. The sun does not owe us its warmth or its light. It simply burns because the physics of fusion compels it to. Yet from that blind process comes everything we value: life, love, beauty, meaning. The universe is not designed for our benefit, yet it has produced us and all that we cherish. This is the deepest mystery of all, not why the sun has sunspots, but why there is anything at all, and why that anything includes conscious beings who can wonder about it. We may never fully solve that mystery. But we can live within it, gratefully and thoughtfully, making the most of the cosmic gift of existence. The sun rises each morning not because it cares about us, but because orbital mechanics and nuclear physics make it so. And we wake each morning to greet it, not because the universe demands our gratitude, but because gratitude is part of what makes life meaningful. Sleep now, with gratitude for the day just past and hope for the day to come. The sun will rise tomorrow, carrying its dark spots and bright flares across the sky. You will wake to its light, as humans have for hundreds of thousands of years, and the great cosmic story will continue, with you as one of its countless characters. The giant sunspot keeps its secrets. The scientists keep their watch. The universe keeps turning. And you, small and brief, but infinitely precious, keep living, breathing, wondering. That is enough. That is more than enough. That is everything. Let the stars wheel overhead as you sleep. Let the sun prepare its morning entrance below the horizon. Let the giant sunspot evolve according to the physics of plasma and magnetism. Let the world turn, as it always has, as it always will. You are home. You are safe. You are part of something incomprehensibly vast and beautiful. Rest well. The cosmos will be here when you wake. And when morning comes, perhaps take a moment to notice the sunrise, not just as background to your morning routine, but as the daily miracle it truly is. The sun clearing the horizon is a sight that billions of humans before you witnessed, a sight that connects you to every generation that has ever lived. Your distant ancestors watched the same sun rise over African savannas. Your medieval forebears saw it climb above castle walls and cathedral spires. Your great-grandparents greeted it on farms and in factories. And now you see it, the same fusion furnace that has warmed every human face, shining on your world today. The continuity is profound. The sun that rises tomorrow is the same sun that witnessed the first life on Earth, the first creatures to crawl onto land, the first mammals, the first humans. It has been present for every moment of earthly history, a constant witness to the drama unfolding on our small world. When historians speak of human events as being witnessed by the sun, they speak a deeper truth than they perhaps intend. The giant sunspot will eventually rotate it out of view as the sun turns on its axis. In about 2 weeks from when it first appeared, it will disappear around the western edge of the solar disk. It may fade and dissipate during that time, or it may persist and return for another transit of the visible face. Some sunspots last for months, rotating around the sun multiple times. Others appear and vanish within days. Whatever happens to this particular sunspot, others will follow. The sun is approaching the maximum of its current cycle, a time of heightened activity when sunspots are most numerous and most likely to produce significant flares and CMEs. Over the next few years, we can expect to see more giant sunspots, more spectacular auroras, and more concern about potential impacts on our technology. This is normal. This is what the sun does. Learning to live with it, to appreciate its gifts while preparing for its occasional violence, is part of what it means to be a technological civilization orbiting an active star. We have the knowledge and the capability. What remains is the wisdom to apply them. May we find that wisdom. May we prepare thoughtfully and act prudently. May we continue to study the sun with curiosity and wonder, learning its secrets while respecting its power. And may we remember, always, that we are part of something much larger than ourselves, a cosmic story that began before there were stars and will continue long after our sun has faded to a cold, white dwarf. The night embraces you now. The stars shine down, each one a distant sun with its own story. The moon, if it is up, reflects the sunlight that has travelled so far to reach it. The earth turns slowly, carrying you from darkness into light and back again, as it has done for billions of years. You are cradled by the cosmos. You are held by gravity, warmed by starlight, made of atoms forged in stellar hearts. Everything you are came from the universe, and to the universe everything will eventually return. This is not tragedy but transformation, the endless recycling of matter and energy that has built galaxies and worlds and life itself. The giant sunspot is part of this cosmic dance. Its twisted magnetic fields, its potential for eruption, its dark presence on the brilliant solar surface, all of it is matter and energy following the laws of physics, the same laws that govern everything from the smallest atom to the largest galaxy. There is beauty in this universality, a deep elegance in the fact that the same principles shape phenomena across such vastly different scales. Sleep now, and let these thoughts settle into dreams. The sun will keep its watch through the night, hidden below the horizon, but never truly absent. Its light, even now, is illuminating the other side of the world, warming faces on distant continents, powering the photosynthesis that produces the oxygen you breathe. The world is connected in ways we rarely see. The sun connects us all, human and animal, plant and microbe, ocean and atmosphere. The giant sunspot, dark though it appears, is part of this connection, part of the magnetic heartbeat of our star that pulses through the solar system. Tomorrow, the exploration continues. Tomorrow, there are new questions to ask and new wonders to discover. But tonight, rest peacefully. The cosmos is patient. The sun will rise, and you will greet it, as humans have greeted it for 100,000 years, with eyes open to wonder and minds ready to learn. Rest now. The cosmos keeps its patient watch. And the story of the sun and earth continues, one day at a time, one sunspot at a time, one human life at a time, into a future we cannot see but can hope to shape. Good night, dear listener, and sweet dreams under starlight.